Okay, well, thanks for the introduction. This is going to be a presentation about GPRS, Edge, UMTS, HSPA, and other acronyms that exist in the cellular data communication world. Let me start with sort of a rhetorical question. How many people in this room have never used any of these technologies? Okay, that's one lone. Okay. The point that I'm trying to make is that this is not a presentation about some cool hacks or some exploits or some security issues or anything like that. It's just a talk about how some technology works. And I think the last time that I remember such types of talks was probably something like 10 years or longer ago at the CCC, where we had something like TCP/IP introduction, right? And this is probably the same kind of talk, but for entirely different protocols, which are not any newer, at least some of them are not newer than these talks that we had 10 years ago or something. But I think it's sort of a mystery and a problem why there is technology that's so widespread. There are literally more than 1 billion terminals out there on this planet that speak at least one of the protocols outlined in this presentation, and yet there are very few people who actually understand how this works if you go beyond the user traffic. Of course, well, if we use a mobile phone to transfer internet data, TCP/IP data, then of course everyone understands the TCP/IP layers on top, but what about the, 5 to 7, maybe 10 layers below that? Who understands them and who does something about them? Okay, well, let's start with a slightly historical excursion. CSD, I'm not sure how many in this room remember what CSD is. It's circuit switch data. And it was the first technology in digital cellular telephony systems to transmit data between terminals, not voice. So GSM is the first, to the best of my knowledge, is the first digital cellular system. It was developed in the 1980s. That's something you always have to keep in mind. This goes back a very long time. GSM has first been deployed around 1990. And it's a pure circuit switch technology. So if you're correct, or if you're true to the word, then GSM does not have any data capabilities except a CSD. We'll get to that. Circuit switched means it's like a voice call. You dial a number, you establish a connection, and then you exchange data. So CSD sort of emulates the behavior of what people used in the 1990s, like modems on the public telephone network. And the data rates that you can achieve using CSD are sort of funny today. It's 2,400, 4,800, and so on, bits per second. It's not megabits or kilobits, bits, whole bits, not half bits or quarter bits. I'm mentioning this because GSM on the lower layers has lots of quarter bits. Okay. Now, CSD is still supported by some operators today, but I'm not really going to cover it for the remainder of this talk. This is just, this is where all this is coming from. It's circuit switched, it's not packet switched. That's sort of the important thing to notice. Then there was HSCSD. I'm not sure how many people remember that. It's channel bundling CSD. So imagine CSD is like you have an analog phone line and 2 modems on the ends, and you communicate, and now you have 2 or 3 or 4 of these phone lines, and you get the aggregate bandwidth of them. It's not very surprising. So there was the option to run 38.4 kilobits and 57.6 kilobits, both very popular data transmission rates in analog telephony systems using modems. So HSCSD was able to deliver those bandwidths over GSM. However, it was very expensive because, well, if you occupy 4 circuits in a circuit switch systems, you have to pay 4 times the amount of money, of course. And also you get 4 times the amount of load. So yeah, I think it was popular for a very short time. I still have a couple of phones that support it, but it's dead ever since GPRS came around. Now, GPRS, the General Packet Radio Service, was specified almost a decade later than GSM. And first deployed in a production network in 1999. GPRS is not an extension of GSM, really. It is a separate network that just shares the same TDMA structure, the same modulation, the same channels, the same bandwidth, and so on. But logically, it's really an entirely different network. And your phone can register to GSM, but not to GPRS, and vice versa, because those are two independent activities and two independent transactions that end up at different units in a network. The reason for this design is that GSM networks had already been deployed for about 10 years before GPRS came around. And now the engineers had the task of sort of implementing a packet radio system that can reuse as much as possible on the radio transmission side, the same modems, the same, same TDMA structure, and so on, but add these services without making too many modifications to the very well working and stable circuit switch side. So this is why there is a different infrastructure for that. The base stations are the same, but anything beyond the base station is different in a GPRS network. It's packet switched, not circuit switched, so it's the first cellular technology that, a digital cellular technology that allows you to send packets where you don't need to allocate an entire circuit of dedicated bandwidth for your data session. The bandwidth was around 56 to 114 kilobits per second. You cannot really say that very clearly because it depends on the exact multi-slot class support of the mobile station and the base station and various other aspects, so it's in that range typically with most of the phones. It's available, it was and is available virtually anywhere on the world except Japan and Korea, because they had different 2G, 2.5G systems. Now, edge. Many people talk about edge. Edge means enhanced data rates for GSM evolution. You will notice that evolution is an extremely important term in cellular technology because everything is always either evolved or evolving or evolution. So it's, yeah. So technically speaking, edge is a superset of what people think it is. Edge consists out of eGPRS and eCSD. But eCSD almost nobody knows, and most people just think of eGPRS when they say edge, or actually, well, they think of edge, but they mean eGPRS. eGPRS now means we use the GPRS network, but we add a little bit in terms of a different modulation scheme and in terms of slightly different channel coding. And we get higher bandwidth than the old system. It uses the same radio channels, the same bandwidth, the same time slots, everything is like GPRS, but it uses 8-phase shift keying, 8 PSK, instead of the Gaussian minimum shift keying that GSM does. There are no real changes to any of the higher protocol layers, except some small information elements where you signal the availability of this system. Otherwise, it's entirely the same. Most phones support something like 236 kilobits per second, and again, like GPRS, it's available almost anywhere in the world. Now, UMTS, I'm just going through the history first, and then we look more in detail into the individual systems. Well, there are obviously multiple typos in this slide. I apologize for that. It's the Universal Mobile Telephony system, not sub, just system. It developed around 96 to 99. So once again, it's sort of developed at the same time as GPRS, but for UMTS, since it's a completely different system, people needed new phones, and so it was expected to take a longer time to pick up, and it was new, more expensive technology, so it was sort of rectified to develop GPRS and UMTS in parallel. First commercial deployment also was 3 years after the first commercial deployment of GPRS networks, and UMTS in its core specification actually also doesn't really have that high data rates. It's 384 kilobits downstream and downlink to the phone and 128 kilobits on the uplink. It's not all that exciting if you think about it. It's an entirely new system. It's not a logical sort of extension or enhancement of the previous systems, but it's an entirely new system. It's based on a modulation scheme called wideband CDMA, where CDMA is code division multiple access. And especially in the US, people always say it's a WCDMA network, which is correct to some extent, but there are many other WCDMA systems which are not UMTS, so it's sort of an overgeneralization. It supports circuit switched and packet switched services. So in UMTS, from the very beginning, they were looking at developing a protocol and developing a system that can work for both circuit switched services and for packet switched services. Unlike GSM, which was entirely circuit switched, and then they had GPRS, which is entirely packet switched, and so on and so on. The fixed part of the network heavily uses ATM over synchronous digital hierarchy systems. So the lower layers of anything that does not go over a radio interface, as you will see in the next couple of slides, is almost always ATM based. So there you can see it's developed in a community where people thought OSI protocols are a great thing and ATM are a great thing, and all this strange IP and Ethernet stuff that other people do is sort of amateur crap. Okay. Now, HSDPA is introducing a couple of new downlink channels. It's high-speed downlink packet access. It's the HSDSCH, the high-speed downlink shared channel. It was added in UMTS release 5. The specifications are released in releases, and they are numbered up to 98. They were based on the name of the year, so there's release 98 or release 99, which are released in the respective year of the calendar, but the further numbering does not necessarily correspond to any year. Some other physical channels that are sort of below this new channel, and it introduces adaptive modulation up to 64 QAM, so relatively complex modulation schemes, and initially permitted 3.6 megabits second downlink. And it also increases the uplink a slight bit from 128 to 384, but it's also not that impressive. HSUPA is actually called EUL, Enhanced Uplink. HSUPA is a marketing term from Nokia. And it uses similar techniques as HSDPA, but in the uplink direction. 5.76 megabits is sort of the... Then there's HSPA Plus, which is the latest extension to those standards, which was added in release 7 of the specification, and it permits up to 84 megabits in downlink and 22 megabits in uplink. By using MIMO techniques, QAM64, and also by combining actually two cells. So a single phone can use two cells simultaneously in order to extend the bandwidth beyond what a single cell could provide. So the theoretical maximum of 186 megabits, which is theoretical, of course. But nonetheless, it's fairly impressive what they managed to squeeze out by evolving the UMTS technology further and further, without going into LTE, the next one around. Okay, now let's look at these individually in a bit more detail. At CSD, I'm skipping, it's not really all that interesting. Let's look at our standard diagram of a GSM and GPRS network. We have our mobile phone somewhere over here on the left-hand side, which connects over a radio interface called the UM interface to a device called the BTS, the base transceiver station. From there, it's backhauled over typically an E1 line, running a set of protocols called ABIS, to a device called the BSC, the base station controller, which connects to something called the PCU, the packet control unit, which then in turn uses another E1 line with another set of protocols called the GB interface to the serving GPRS support node, the SGSN on the bottom here. The SGSN is taking care of mobility management, encryption, compression, and all kinds of things for the actual data that gets transmitted to the phones over here. Also, authentication is handled by the SGSN in GPRS. And the SGSN then connects over a GN interface to the GGSN. The GGSN is the gateway GPRS support node, and it's where the IP packets the tunnels terminate towards the internet. So those entire nodes in this network establish transparent tunnels between the GGSN and the MS, the mobile station, the phone on the other hand side. The GGSN is the only IP-only device in the network. Everything else is not really doesn't really deal with IP. There's just some user data which we encapsulate somehow, and we wrap it enough so we don't really have to touch the IP. It needs to be properly wrapped to be able to transport it over our ATM and E1 and SDH and whatever other technologies. So if you look at the control plane stacking, what's the control plane? Well, the control plane is anything that's not your user data. Control plane is about setting up connections, authentication, taking care of handover, mobility management, all these kind of things. That's the control plane. And the user plane is where you actually have your IP data, your internet data that you want to transmit. Now the control plane, let's first explain the diagram a little bit. We have the individual nodes listed here. There's the MS, the mobile station. It's not Microsoft, it's the mobile station. It may run an operating system from Microsoft though. There is the BTS and the CCU, the circuit control unit, which is the node represented here. Then we have the BSC, the base station controller, and the packet control unit, the SGSN here. And for the control plane, I didn't put the GGSN here, but for example, the HLR, which is where your subscriber data is stored and also involved in for example, it lists what kind of services you have subscribed to or not. This kind of data is stored in the HLR over here. Now the dashed lines are the individual interfaces between those nodes, and the interfaces have always these strange names like UM, ABIS, GB, GZ, and GN, and all these small names. Now, as you can see, there's a physical layer. The physical layer exists over the radio interface between the phone and the BTS. And then we have other protocols on top. There's a MAC, an RSC, and LLC protocol. The two lower ones, the medium access control and the radio link control, RLC and MAC layers, they terminate in actually the PCU here, the packet control unit. And they're transparently passed not only over the radio interface here. This is your only radio interface. It's the UM interface, and this is typically an E1 type line here on the backhaul, and they're transparently passed over here. They terminate in the packet control unit, which then re-encapsulates the payload, which is LLC, Logical Link Control Protocol. It gets encapsulated in a new protocol called BSSGP, the Base Station Subsystem Gateway Protocol, which gets then encapsulated in the NS, I think it's Network Service Protocol, which then gets put into frame relay, which gets put on top of an E1 line. And then it gets backhauled to the SGSN, that's a sort of a centralized node in the network, which then implements this entire same stack here, E1 with frame relay, with NS, with BSSGP, but then also terminates the LLC layer, which is coming directly from the mobile phone. And then on top of that, we have two sub-layers called GMM, GPRS Mobility Management, and SM, which is not what you think it is Session Management. All these terminate here, basically. There's nothing that doesn't terminate at the SGSN in the control plane. And then towards, for example, oops, sorry, that's the next slide, towards the home location register, which is like your subscriber database, there's an entirely different set of protocols, usually referred to as SS7, but more specifically, it is an E1 line with MTP level 2 on top. MTP is message transfer part. MTP level 3 on top. SCCP on top. TCAP, the transaction capabilities application part, and then map the mobile application part. Those exist on completely different interfaces. So what you can see from this is that each and every interface has a completely different protocol stacking. These protocols are independently specified. They're most often specified by different working groups. You can see, when you read the specs, you can clearly see it's written by different people. They do not, use the same encoding. They do not use the same information elements and so on. So each of those protocol stacks is an entirely different beast that you encounter depending on the interface. Now, this is the control plane. Now, I'm going to talk about what happens on this control plane just in another slide. I'm just going to go through the user plane to show you how deep the stacking actually is. Now, let's assume you make on your smartphone, you do an HTTP request that gets into TCP, of course, gets encapsulated into IP, which then gets encapsulated in my favorite protocol. It comes straight out of Star Trek. It's called the Sub-Network Dependent Convergence Protocol, the SNDCP. You have to, Scotty, you have to remodulate the Sub-Network Dependent Convergence Protocol. It wouldn't, it's, we have fluctuations in the BSSGP. No. So, the SNDCP, then the LLC, then the RLC, then the MAC, and then we finally can transmit it. And almost all of them get transparently passed through the BTS. Some of them then terminate at the packet control unit here. Another couple of them on the SGSN, and finally the user data gets passed over to the GGSN, where it can enter, how can I say, the strange world of IP-based networks. So when you're thinking about all your, I don't know, web vulnerabilities or whatever kind of higher level application level stuff, you're up here, and there's lots of other stuff which a lot of people don't really look at in detail. Below. Okay, now what are these individual layers? Medium access control, sort of, I mean, almost every physical layer has a medium access control layer. I don't need to say much about that. These numbers that you can see, the like 44.060, I put them in here for a reference. So if you want to learn more about these respective layers, this is what you type into Google or your favorite search engine, or you go directly to the 3GPP website and look up this specification. It's on top of what's called a PDTCH, a packet data traffic channel. It's a physical channel on the air interface. And on top of MAC, you have RLC, which takes care of, well, radio link control is the name. Sorry, there's too many typos in those slides. I apologize, I will fix that immediately. The resource allocation, like which phone gets how many time slots and gets which amount of bandwidth and so on, is always determined by the network, of course, right? It's not like some random arbitration or like you have on Ethernet where you have something like CSMA CD and everyone can just try to send packets at any given point in time. No, no, no. This is not an unorganized Ethernet network. It's a very well structured, well thought through professional communications protocol. Because it's so professional, of course, it cannot rely on, I don't know, human readable message definitions. The messages have to be specified in a syntax, in an abstract, well, no, actually not in an abstract syntax, but in a parsable, machine readable syntax. And because there weren't enough of these syntaxes so far, they invented something called the CSN1, the concrete syntax notation, which is very different from ASN, the abstract syntax notation. So it's much more concrete in a sense. In the sense that, you know, in ASN1 you have the syntax and you have the encoding rules, and that's not very concrete. So in CSN1 there's no separation between the two. There's only one possible encoding, and that's part of the specification. By the way, the specification costs something like 10 euros, and it's only available printed, and you have to order it from France and have to do a wire transfer to their bank account and so on. It's quite funny. I mean, I think the amount of overhead they have for charging these 10 euros is sort of, well. Okay, now the GB layers. GB is again the interface between the BTS and the BSC/PCU. There's the network service layer specified in 0816, which sort of maintains possibly redundant set of physical links on top of frame relay. It does things like failover and load sharing among multiple links because sometimes one E1 line is just not enough. You need multiple of them, and then you need to somehow share the load. It's originally specified over frame relay, but sometimes actually people put a Cisco router behind it to encapsulate the frame relay in IP. So then you have Then you have the entire stack that I indicated, where is it? Here. Well, something like this stack up to NS in frame relay, in some other encapsulation in IP and some other layers on the bottom. But then some other people also came up with the bright idea of putting NS directly into IP, well, sort of via UDP, so you can skip the frame relay part if you want. Now, on top of that, there is BSS-GP, which maintains things called BSS-GP virtual connections, BVCs. And each base transceiver station in your base station subsystem now establishes one logical connection. It's called a BVC, a BSS-GP virtual connection between the SGSN and this BTS. BSS-GP also implements flow control, and it's actually a hierarchy of of token bucket filters, which are sort of encapsulated into each other. So there is one flow control for all the data going to one BTS, because of course you have an E1 link, and at some point you might saturate that, so you need to have flow control on the entire link. And then you have flow control for each individual mobile station that connects to that BTS. And then you can have individual packet flows inside contexts of each individual phone, which again have these flow control. So you have this hierarchy of 3 levels of flow control that make sure you're not flooding the BTS with packets coming from the high bandwidth internet, which want to squeeze through the tiny radio interface between the phone and the network. Because you have your bottleneck here. That's typically your bottleneck is the radio link here. But the packets, of course, come in from the internet over here, and somehow you need to make sure that you're not flooding that link in a completely unfair or undeterministic way. BSS-GP is extremely inefficient if you think of it in terms of overhead, because each and every BSS-GP message, which is each and every of your TCP ACKs, let's say you have a TCP ACK packet, it's like 20 bytes TCP header, plus 20 bytes IP header, plus a little bit of SNDCP header, plus a couple of bytes LLC headers, plus a frame check sequence of 32 bits at the end of LLC, plus the BSS-GP header. And the BSS-GP header now includes the full IMSI, the full radio access capabilities information element, which can easily be something like 30 bytes. So in the end, you want to send a single acknowledgement back to your phone, and on these interfaces here, you might easily say, see 100 bytes or even more for the single acknowledgement. So that's just something to keep in mind in terms of efficiency. Okay, now on top of that, we have my favorite, as I said, SNDCP. Well, SNDCP is too many typos in here. LLC is between SNDCP and the lower layers. Let's talk about LLC first. It supports acknowledged and unacknowledged mode, but normally for IP communication, it's mostly used in unacknowledged mode. LLC actually, you might have heard in different contexts. I think LLC goes back to IBM mainframes, actually, where in SNA networks, LLC was one of the protocols used in those networks. It's though a different, a specific variant for GPRS networks that we have here. The encryption of GPRS happens on this LLC layer, and as well checksumming of the frames also happens on this layer. SNDCP now is on top of that, and it's a general purpose encapsulation for the packet data, because when GPRS was designed, once again, remember the mid-1990s. I mean, a lot of people were already using the internet, at least that's how I remember it. But in the cellular industry and in the professional communications industry, they were still thinking of X25 and the OSI protocols and all the marvels of X400 and all those things. And it was designed in a way that it can transfer IP as well as other protocols such as X25. So you can actually have X25 over GPRS in accordance with the specifications. If we actually look at IP today, the SNDCP also takes care of IP header compression. and also possibly V42 payload compression. There can be arithmetic compression of the data built into this level. If you look at the control plane, what is GMM? GMM is mobility management, which, well, is like mobility management GSM. If you know about that, then it's easy to guess what it does. It doesn't use SNDCP, only LLC and the remaining part of the stack. It's responsible for things like routing area update. This basically is your phone telling the network where it currently is located. Things like attach and detach, when you switch on and switch off your phone or enter airplane mode or leave it. It also does take care of authentication, which is the same authentication method that GSM uses, using the same keys, by the way, and the same algorithms. It also reallocates the temporary identifier. GSM has a TIMZ, GPRS has a PTIMZ. It's also something important. Anything that's if you look at GPRS, everything has to start with a P. So you have the TCH, the traffic channel in GSM, and you have the PTCH, the packet traffic channel in GPRS. You have the BCCH in GSM, and you have the PBCCH in GPRS, because it's the packet broadcast control channel. There's also a provision for delivering SMS over GPRS, and if you look at only the layer 3 transactions between individual nodes for performing a routing area update, it looks a little bit like this. First, you have your layer 1 establishment, then you establish the RLC MAC layers, and then on the LLC level, you encapsulate the GMM messages, like routing area update request, gets sent from the phone to the SGSN. Oops. Then the SGSN behaves a little bit like the MSC in GSM networks. So it can do, for example, identity requests. It can ask the phone about its IMSI, its IMEI, that kind of stuff. And then on the backhand side, just like an MSC would do it in the circuit switch world, it can ask the HLR and AUC to provide authentication information for performing the cryptographic authentication, which is then performed here. And then on the map interface here to the HLR, we see the location update request, insert subscriber data, and so on. So really, if you know how an MSC behaves in a circuit switch network, just replace MSC with SGSN, and most of the time things are pretty much the same. The next thing is session management, which establishes and maintains the tunnels to external packet data networks. So they don't talk about tunnels. Everybody, I guess, in this room knows what an IP tunnel, a VPN tunnel, and so on is, but most people don't know what is a PDP context. It's exactly the same thing, it's just that they use a different name. And of course, it has to start with P. So it's a PDP context, and it's not related to PDP-11. You can have multiple of these contexts active at any point in time. So actually, it's not that your phone can only have one connection to the public internet, but you can have a number of different tunnels, possibly terminating in different IP networks. It doesn't have to be the internet. I mean, there are many other options available. For example, there are companies that operate M2M devices over GPRS. They quite often have their own tunnel endpoint, their own GGSN, and so the IP data doesn't end up in the internet, but it ends up directly in their own IP network, which is not a public network. The resolution of where do you connect to, which tunnel broker, which is called GGSN, do you use is done by the APN, the access point name. The mapping from access point names to IP addresses of the GGSN is done by using DNS, and they have private DNS zones which are accessible only to the GSM operators for resolving those names and IP addresses. And then the tunnel establishment is passed to that particular GGSN. If you look at that procedure, you have channel establishment and so on and so on, and you see something called a PDP context activation request, which is a phone saying, I want to have an IP tunnel established now. The SGSN will then make a DNS query on the APN that was specified by the phone, so like internet.e+.whatever or something like that. There will be a response to that DNS, hopefully, the request, and then the SGSN establishes a GTPC connection to the GGSN and forwards that context activation request, and it will be acknowledged. Hopefully the acknowledgement will be forwarded, and then from that point on you actually exchange IP packets between the GGSN and your phone. This GTP protocol is once again specified in one of these fancy specs, 29060. It's the only protocol at that time which was specified over IP networks right from the beginning. The idea was that the GGSN is a pure IP device. It doesn't have to have E1 connections. It doesn't have to have an SS7 stack. It doesn't have to have any of these fancy things. That's why Cisco built one of them. Because, well, you know, they wanted the IP network vendors, the router and switch makers to be able to build these devices. GTPC, the control side, is used for this tunnel setup and teardown, and the user plane GTPU for actual user data. On this interface, there's no authentication, no encryption, because it's only intended to be used in intranets or inter-operator links that are private anyway. So might not be always the case, but at least that's how it was intended to be used. Okay, so far for GPRS. Let's move into more current technologies. UMTS packet-switched systems. The higher layers like GMM and SM are actually reused from GPRS. There's no change on them. This is like the circuit switch domain. Also, the core control, for example, that existed in GSM is reused one by one in UMTS. But all the other layers below, they're really very different. Most of the SGSN remains the same, the GGSN remains completely the same, but anything that relates to the radio access layer, to the BTSs and so on, is not only different, but is also called completely different. So there's no BTS, there's a Node B, there's no BSC, there's an RNC, so all these things. The mobile phone is no longer the MS, it's now the MT. So it looks a little bit like this, at least if you use graphics that are available online. You have Node Bs, these are your individual cells, which are connected over a link called IUB to the RNC, the radio network controller, which then connects to the SGSN here over an interface called IUPS, the IU interface for packet-switched PS services. If we look at the protocol stacking, we will see some names that at least sound familiar, like MAC and RLC. They are different in implementation, though. Would have been too easy. We see a new protocol called RRC, the radio resource control. On top of that, we have familiar names. GMM and SM are just the same. On the bottom half, we have lots of new stuff that comes in because it's now ATM and not frame relay or E1. Or it might be E1 physically below the ATM, but at least no frame relay. So you have all these adaptation layers. If you've heard about AAL2 and AAL5, some people may be old enough to still have learned that in university. These are all adaptation layers, how you can encapsulate stuff on top of ATM cells and ATM virtual circuits below. This is again the only radio interface that's specified, and you can see again the Node B doesn't really do anything. It just passes stuff onto the wired interface here, onto IUB, to the RNC, which is what used to be the BSC in older networks, where MAC, RLC, and RRC layers terminate. RRC is translated into a different protocol on the same level called RANAP, the Radio Access Network Application part. Then RANAP is forwarded over SS7 actually, so you can see here MTP3B for wideband ATM links with SCCP on top, or alternatively using a IP and ATM and then an SIGTRAN kind of stack up here. So RANAP goes back to the SGSN, where also again SM and GMM terminate, and the remaining part is just the same like in GPRS. If you look at the user plane, there is one new protocol also, is the PDCP, the Packet Data Convergence Protocol, I guess. Then again, you can encapsulate your higher level protocols inside the PDCP protocol. MAC layers are specified in some specs. They have fancy numbers. The RSC takes care of encryption. So the encryption is one level lower than in the GPRS networks. Also takes care of segmentation, retransmission, and so on. Interestingly, the RSC layer is not specified in any formal syntax, which in UMTS at least is very uncommon. So it's just like an IETF RFC for common protocols you find on the internet, where there's a human-readable description, but not a formal syntax describes the messages. However, the next higher layer, the RSC layer, is again specified, but not in CSN1. This time they switched to ASN1 and use packed encoding rules, PER, in order to avoid the overhead that BER or DER would bring with itself. RRC itself takes care of measurement control, ciphering control, paging, radio bearer management, so which channels to use and so on, broadcasting system information, and also has integrity checking. The RRC corresponds to the RR layer on GPRS. The PDCP is the replacement for SNDCP. Not quite sure. They could have used SNDCP. I don't really see much difference between those protocols, but they just are different and have a different name. It handles user data payload and header compression. There is a new compression scheme, ROHC, that GPRS doesn't do. It's robust header compression. It allows you not only to compress the TCP and the IP header, but also RTP. So it's optimized for doing voice over IP, so you can compress away not only RTP, UDP, and IP headers, and get rid of some of the overhead involved. It's between the user IP, the PDCP is between the user IP and RLC. If you look at this, it's here in that layer. It's what comes below your IP messages. The RANAP protocol is between the RNC and the SGSN. It's again specified in ASN1, also uses PER encoding, never visible to the user. However, the Vodafone UK and Alcatel-Lucent femtocells use RANAP also to the femtocell. So if you're into looking at those devices, you will find RANAP in there. There's also something called NBAP, the Node B application part, which then is between the RNC and the Node B. Again specified in ASN1, again not visible. However, there are some Node Bs that sometimes you can buy from eBay. And if you buy a real Node B, then you will have to implement that protocol to talk to it versus RANAP, which you need on the femtocells. It's actually quite funny. I wouldn't have thought that a year or two ago that you can buy large UMTS base stations now on eBay, but it's not horribly expensive. So sometimes it's like 1,500 euro or something. It's not cheap, but if you consider that from this BTS you can serve something like 240 concurrent voice calls or something, it's quite impressive actually to find those devices. They often come from places like Singapore or Russia or the United States. Not sure, in continental Europe you don't see that many being sold. Okay. The GTP layer between SGSN and GGSN is the same as in GPRS. There's no real change. Some new information elements or something, but that's really it. There's no change at that point. Now, if we look into HSPA+, the problem is if you go to the data rates that I've indicated, like these 180 megabits theoretical maximum for a single base station, bottleneck, of course, becomes the SGSN because it's a centralized node where all the user traffic goes to, because the SGSN takes care of the compression, decompression, encryption, decryption, retransmissions, and so on. I think the fastest that I've seen you can buy is 40 gigabits throughput, but most of them are actually smaller. And if you think about a network, like a nationwide network in Germany has about 20 to 30,000 cells. Well, if you think each of them would have a load of 20 megabits or something like that, you will see that this is not sufficient. So HSPA Plus change in a way that basically move a small SGSN into each node B. And then they talk GTP directly to the GGSN, which is not even on that picture. They move core network functionality out to the edge of the network in order to distribute the load that's created by those high bandwidths. So the segmentation, compression, encryption is no longer on a centralized node, but it's at the base station at the edge of a network. That's a fairly significant change to the centralized architecture that we had before. Okay, well, that's sort of my quick run through the various protocol stacks. As you can see, there are many acronyms on the slides that I didn't even mention. And there's many more things that could be said and that can be learned. And there's more than 1,000 PDF files, which each hundreds to thousands of pages, which are ready for you to read. I encourage everyone to go where most people have not gone yet, which is to look at cellular protocols and learn about technology and play with technology and not just leave it to Nokia, Siemens Networks, Ericsson, and Huawei to do that for you. Okay, thanks for the attention. We have some time left for questions.
Okay, so we have about exactly 15 minutes for Q&A. Please, all of you, remain seated while we are doing the Q&A session, because it interrupts the speaker and the rest of the audience who wants to listen. If you have questions, please line up at the 2 microphones, as always, and Harald will answer your question.
Hello. A couple of points. You said that everything is ATM all the way to the Node B and everything, but in my experience, at least new installations will definitely use IP all the way, because SDH and ATM are expensive and bad. So I'm not sure if that's a bit dated or what.
It is indeed correct that more current equipment is replacing ATM with Ethernet over fiber optics with IP inside. That's true, but I didn't want to make it even more complex than it is in the diagrams. Nevertheless, there's still a lot of equipment out there that runs on ATM, and it depends a bit on the region. If you think of Western Europe and the US, I think the synchronous networks are more expensive, but if you think of the less developed world, then they want the TDM style networks still. Even today, they don't want anything else.
Yeah, 2 more points. Oh yeah, the 3G DT, I don't know if you use that term, but terminating the GPU in the RNC. And I mean, that's something you can, that's been implemented as well. So it doesn't always go through the SGSN or the mini SGSN in Node B.
Yes, that's correct. I mean, I did not claim that this presentation is a full, comprehensive overview about all the possible configurations of networks. But yeah, definitely, there are options that you can do for configuring networks differently. I mean, there are always vendor-specific changes. I mean, the reference architecture described by the specifications is not always followed to the last line by the individual vendors. Even in GPRS, the PCU can be located inside the BTS or inside the BSC or co-located with that, and different vendors have different implementations. So, yeah, but go ahead, please.
Yeah, just one funny note on the GTPC protocol. You said it doesn't have any authentication, but there is the 1 bit that says it's cool. I checked with the HLR. I am allowed to connect. The evil bit.
I wouldn't call that authentication, but yes, it's a nice point to raise that there is a bit that says it has already been authenticated. Thank you.
So, Harald, thank you for your talk. A question: why is this so bloated, so much bloated? Because it's so error prone. So if they started to make UMTS, they could have said, okay, let's do a new network that is very simple and would work and is not so error prone. Because if you have all these layers, and they have bugs in the layers and maybe some range checking problems between the layers and the conversation encapsulation, stuff like that. Or you can make a layer, for example, you could embed a protocol inside the protocol, and then if you unencapsulate it, you get the rest of the protocol, and you can fuzz up everything. So if you, for example, fake a protocol in the lower layers and put it in the upper layer, and then it starts to the onion, so the layers, so it puts the layers around away, and then it sees, oh, there's something from the protocol that should be there, and then you can fuzz the stuff.
Okay, I think the number one wrong assumption to make is that these systems are designed to be, I don't know, to be reasonable or to be efficient. I mean, the number one design criterion is every one of the industry representatives needs to make sure that all the patents they hold apply to the specification. So everyone needs to add something to the spec that makes sure that their own patent portfolio is represented in the spec. The next thing is that there is reasonable grounds to the suspicion that it's made artificially complex in order to keep new market entrants and new competitors away, right? Because you have this existing club of manufacturers for equipment, and it's like 5 or 6 companies worldwide. And if they would make something simple, then that would mean every random Joe would be able to implement this stuff. And that's sort of course, it's very useful to have a complex system where only you with your thousands of engineers that know this stuff in and out can actually implement it quickly, and you keep the competition away. So that's sort of thoughts that I would want to give on as a feedback on that.
Well, which brings me to my question. Are you aware of any open source project that working to implement the 3G, something like OpenBSC, but for 3G?
Well, the simple and sort of simple excuse from my point of view, from my side, would be, well, as soon as you write it. But more seriously speaking, for the GGSN there is an implementation, but that's
there's
very,
open
far away.
SGSN and open GGSN, but
if you look at the things here, it's I'm not aware of anyone having done any open source implementations here. There are a couple of people who did some work with femtocells, but it's not really in a way for operating femtocells. It's more for doing man-in-the-middle attacks and that kind of stuff. Mm-hmm. We did some also, I mean, in the Osmocom project, we did some experimentation with all the major femtocell architectures that we found, but it's mainly a question of priorities and available developer time. So definitely it would be very helpful for somebody to work on those things, but yeah, it takes time, it's complex, and we need more people working on this.
Okay, thanks.
Harald, a short question. What about LTE? Will the complexibility be more or less?
Different.
Different, but they do the but they do the whole fucking stacks and big and everything stacked about over each other. They do the same.
LTE. So let me say one thing. All the things that I've talked to do not show you the complexity in layer 1. No? Layer 1 is more complex than any of the diagrams on here. It's the radio layer to the phone. And layer 1 of 3G is already complex, but I think LTE is less complex. Also, it uses less, how can I say, less industry-specific or uncommon, coming from the internet background, LTE is not using so many protocols that are completely unknown to people who have some non-mobile network experience. So it's more IP-based, yeah, it doesn't do all this E1 and ATM and so on crap from the beginning. But nonetheless, then if you look at the security, for example, in LTE, all the different keys and certificates and everything involved, it's already that is, again, fairly complex. So complexity in different areas, maybe.
What about test benches? So all these providers need test benches to test their equipment. And so it would be a huge room of vectors and states that you cannot test. So it would be so complicated that you cannot test the system. And so you get so many bugs that go through maybe 10 years undetected. And so if you do all these complex systems, you will always fall over the bugs.
Indeed, it's a problem. It's a problem that starts to get recognized now. But still, I think there's no specification anywhere, neither from the 3GPP, nor from the GSMA, nor from individual operators that I would be aware of, which would require something like the most simple fuzz testing of any of these interfaces before delivering a product. So requirements-wise, the requirements are always functional requirements. It has to work if everything is correct and if the message comes in like this. But there's never a specification that requires, stability no matter what kind of random crap you throw at it. That doesn't exist. And it's sort of a bit difficult. Dieter and I, we have been in contact with a number of operators to do such kind of tests, and some operators are actually open enough that they want to do that, but they get a lot of pressure from the equipment manufacturers to not do it. So there is an enormous pressure on some of those operators to not do any of this testing on those interfaces, which makes me quite suspicious.
Okay, we have 5 minutes left, so we're going to take some questions from IRC.
Wu-Tang wants to know, how hard would it be to host a man-in-the-middle attack with a fake base station, like an IMSI catcher for GPRS?
Sorry, I didn't understand the question. Could you please repeat it?
How hard would it be to host a man-in-the-middle attack with a fake base station, like an IMSI catcher for GPRS?
Well, so an IMSI catcher is not more difficult than in GSM because it's the same authentication and it's only one-way authentication in GPRS as well. Doing a full man-in-the-middle attack is more complicated, but the question is how realistic do you want to be? I mean, a full man-in-the-middle attack means that you're sitting in between the real network and the telephone and you're passing data from left to right, and you're eavesdropping or you're modifying the content or something like that. That's relatively hard, given the fact that none of the GPRS encryption algorithms so far have been publicly released, disclosed, or anything like that, so it's completely unknown so far. But I would make the point that it's not required to do that because most people just access the internet. So it's sufficient if you set up a false base station and you route the packets to the internet, like a false Wi-Fi access point or something like that. And that's very, very easy to set up.
Okay, another question. What is the overhead added to IP, TCP, or HTTP in UMTS or GPRS?
Oh, that's very, very hard to say because there's so many. First of all, on which interface? On UU, IUB, IUPS, and so on and so on. There are many different interfaces. And the next part is that it's difficult to say because there's compression involved. And the question is, how well can you compress the data or not? So it's not easy to say. But especially in GPRS, the overhead is fairly large. If you think of something like doing VoIP over GPRS or Edge, then you have very, very small messages with your speech codec data, and then all these headers pushed in front of it, the overhead is gigantic.
Thanks for your presentation. Looking at this from the user's perspective, I would do dial-up using PPP most of the time, which actually is the only protocol I'm missing on this slide. Is PPP actually used inside the network, or is it only something I talk to my modem?
It depends. So PDCP or SNDCP, those encapsulation protocols, they have the capability of encapsulating either PPP or IP directly. When you request the PDP context activation from your modem, if you do that by AT plus PD, by IT commands, then you can actually request which one you want to have. On a regular user interface, of course, you cannot. I would expect most of the connections to just use IP, and the PDP that you speak is terminated on the phone itself. But if not, if the PDP is passed in here, then you have an additional layer below here, which is PDP, and it goes all the way back to the GGSN, which then would decapsulate. You don't need PPP for anything really, because IP address, for example, IPCP kind of options for assigning dynamic addresses can be done by PDCP or no, actually it's done by the session management itself. And you can also encapsulate IPv6 directly in SNDCP or PDCP. You don't need that. You don't need PPP really at that point. It would just add some more overhead. I don't see what would be the gain, unless of course you would want to do something like Apple Talk over PPP over GPRS.
Would it be possible to put some very weird protocols, so not IP, for example, puts ISDN over UMTS, or do maybe some what's also ArcNet over UMTS and some stuff? Would it be possible, or is it a problem?
Technically, it's possible. However, you would have to control both the mobile station and the GGSN. And while it is possible as a business, it is possible to get your own GGSN attached to operators if you want to, for example, as the example I mentioned with machine-to-machine applications where you don't want to go to the real internet, but you want to go to your own private network. It's possible to get a connection to this, but it's very expensive and not really done in many cases. So technically, yes, but I think as a regular user, it's not feasible for economic reasons.
Is there an open source GGSN, so you could do some weird stuff?
Yes, there is Open GGSN, which, you could modify. But the phone you would also have to modify, and you would have to attach to that interface, which in a real network you cannot easily do.
Okay, one last quick question.
How many cryptographic algorithms which are secret are still there in GPRS and UMTS?
In UMTS, none. It's all specified. In GPRS, there is GEA1 and GEA2, GPRS encryption algorithm 1 and 2. So I think it's those two, that's really it. Well, encryption. For encryption, yes. Authentication, there are more unknown algorithms. But how can I say? It's unknown doesn't mean it's unknown to everybody.
Okay, we're a little bit under pressure, so we have to stop here. For the next talk, I think we have a small announcement to make. But first of all, let's thank Harald. So, just come up here.